earthquakes. And so many of the earthquakes that happen in the surrounding happen in the Ring of Fire, which is a series of subduction zones in the Pacific Ocean. And this hosts many of the largest earthquakes on our planet. Key examples are the 1960 magnitude 9.5 Good Friday earthquake in Alaska, and the 1964 magnitude 9.2 Valdivia earthquake in southern Chile. So it's good just to know that magnitude 9 plus earthquakes can happen in these examples. They are in Chile and Alaska. And I've highlighted some examples that you may actually remember seeing earthquakes in the news. For example, the 2004 magnitude 9.1 earthquake in Sumatra. And people really learned about tsunamis and their potentially devastating effects during this earthquake. In 2010, there was a magnitude 8.8 earthquake near Male in central Chile. And I'll discuss this earthquake a little bit later. And then very well-known earthquake is the 2011 magnitude 9.1 Tohoku earthquake in Japan. And so this ring of fire is also associated with a large amount of volcanism. And these large earthquakes change a lot of the geology onshore, including a relative sea level change, extensive liquefaction, and landslides. So there's large signal from these earthquakes also on land. These earthquakes cause a significant hazard, both onshore and offshore. We'll discuss this in a little bit detail later as well. And there's a question from the reading: can these earthquakes be predicted? The short answer is no. Earthquakes cannot be predicted. And however, there is something called earthquake early warning, where we can get sometimes maybe 30-second warning before earthquakes will happen by looking at the arrival of different seismic waves. And interestingly, the Tohoku Oki earthquake was so well instrumented, we've been able to see some potential precursors of earthquakes. But again, earthquakes cannot really be predicted. So what happens during these big subduction zone earthquakes? So here on the left is the Male earthquake, which happened just off the coast of central Chile. Here's the plate boundary. And then this color here shows the slip during the earthquake. And so someone asked, how can we, or can we learn about the slip earthquakes that don't rupture the surface, or we can't see their surface rupture? So here's an example where we can use data, for example, GPS or GPS displacements on the coast here to solve for the displacement or the slip along the fault. So looking at this picture, what was the rupture length of most of the slip in this earthquake? Question to the audience.
Can you repeat? Sorry, Chelsea.
Yes, so here, this color is showing the slip during the earthquake. So the white is no slip, and then this dark color is the maximum slip. So the question is, what is the rupture length of these subductions, or this subduction zone earthquake?
15 centimeters? You're asking, or the just below 20 meters.
So yeah, so during the earthquake, there was 20 meters of fault slip. And then my question was, how much of the fault ruptured during the earthquake? So we see here.
That in terms of like 2 degrees of rupture?
Yes, exactly. So we saw roughly from 36 degrees to 34 degrees. So we had about 200 kilometers of rupture of fault length during these earthquakes. So it's just good to keep in mind that these earthquakes do rupture a fairly long portion of the coastline. And then here is the Tohoku earthquake in Japan. It was a 9.1 earthquake, so bigger than the one in Chile. And we see about 4 degrees of latitude of rupture. So these are truly quite big earthquakes. There's another question from the reading of what is a megathrust earthquake. And so these are earthquakes along the subduction zone that have magnitude greater than or equal to 8. So both of these are megathrust earthquakes. If they're along the same fault that have magnitude 7, then could be called a subduction zone earthquake, but not megathrust. So we'll now talk about the earthquake cycle along the subduction zones. So there's 2 main different parts of the seismic cycle. The first one is interseismic, where elastic strain accumulates. So here we have the subducting plate and the overriding plate. And during the interseismic phase, these 2 plates are locked together at their plate boundary. So as the subduction zone plate is pushing to the right, the overriding plate moves up and shortens. Then we have the earthquake rupture, where there's movement here along this plate interface, and that causes both subsidence of the plate along the coast as well as extension. And so all of these signals are important for measuring the effects of these plate boundaries in this overriding plate. So paleoseismology of subduction zone earthquakes. So during the earthquake, this is very quick subsidence, and that causes these coastal areas to essentially become part of a lower intertidal zone where they become buried by sand and mud. And you can do dating on fossilized trees to constrain the timing of the earthquake. So other evidence, good evidence for earthquakes include tsunami sands and liquefaction features. And finally, to really have strong evidence that the signal is an earthquake, you would expect to see widespread changes at the same time from the earthquake. So for example, we just discussed that the earthquakes rupture 2 to 4 degrees of latitude. So we would expect to see these sort of subsident features over a few hundred kilometers. On the first reading, there are actually many questions on dendroseismology. This is essentially looking at earthquake-killed trees, sometimes called ghost forests. And this turns out to be a very sensitive record to subsidence. So here is a picture showing the 1964 earthquake in Alaska, where the coastline subsided and the submerged trees continue to grow for 1 to 2 growing seasons with stunted growth, and then they died. And this technique has been very important, particularly along the Cascadia earthquake margin, for assessing the timing, location, and therefore also magnitude of the last major earthquake along the plate boundary. So also a term upper plate deformation, and this refers to the deformation that happens here in the overriding plate. This area is very important because many cities are in the coastal ranges and the forearc. This includes in the US, we have Seattle and Portland, and then internationally, Vancouver, Tokyo, and most of Chile, including Santiago. So when looking at the faults that rupture this portion or the coastal ranges in the forearc, there's a few interesting questions that scientists often ask, which is what is the recurrence interval of these earthquakes? So it often seems to be much longer than the 300 years or so recurrence interval of big subduction zone earthquakes. Second, do subduction zone earthquakes trigger upper plate deformation? In other words, are these earthquakes more likely to happen after a big earthquake or megathrust earthquake? And finally, how do the kinematics of these upper plate earthquakes relate to the subduction zone? So I'll go over several examples of upper plate deformation. Or actually part of my thesis looking in Chile and Argentina. So it's first an example of surface fractures in the Chilean coast range. So here we're in South America, very northern tip of Chile. This is the Atacama Desert. It's the driest non-polar place on the planet. So there's no trees. Cannot look at these submerged forests to learn anything about the plate boundary history. But it turns out that these fractures provide very similar information. So here you can see these very delicate surface fractures that have ruptured or formed or reopened during a magnitude 8.1 earthquake. Recent earthquake just off the coast of northern Chile. And if you look at these fractures for long enough, you can use their orientation and their strain to also estimate the location of average large earthquakes along the plate boundary, somewhat of a similar way to how we can use the submerged trees. So now we're going to go down to central Chile, just looking at the magnitude 8.8 2001 or 2010 earthquake in central Chile. And this earthquake triggered a lot of seismicity, which we can see here in the far field. Particularly, I spent a lot of time studying this earthquake here in Salta, northwestern Argentina. In this location, INSAR stands for interferometric synthetic aperture radar, is a very good way of measuring the surface deformation. So here is where you can see the earthquake. Actually, this earthquake didn't rupture the surface. There's another question in the reading of how can we learn about earthquakes that don't rupture the surface? So these earthquakes still produce displacement, which we can measure to learn about the earthquake's location, depth, and focal mechanism. So here, yes, again, summary, we see this example of earthquakes that occurred within 1 to 2 days following the Male earthquake that represent very much elevated seismicity and were likely triggered by this big earthquake just off the coast of central Chile. And so for homework 2, you will get to look at upper plate deformation in Seattle. So here's an example from a hillshade of a digital terrain model from airborne LiDAR. So as many of you probably know, Seattle is many trees, and it's difficult to see through these trees with aerial photography. But as you'll learn, we can use LiDAR to essentially see the trees or see through the trees. And this highlights a number of geomorphic features that we can use to map and understand the tectonic geomorphology. So that is my presentation.
How about some questions for Chelsea?
Are you aware of the massive earthquake yesterday and the series of earthquakes that followed?
In Chile,
Yeah.
I briefly saw them, saw that they were in the north, but haven't looked too much more than that.
Yeah, massive. I would say that a 6.9 is massive, not in that system.